understand how do you go about this problem, how do you solve this problem. What is the main question is, what should be your displacement measure? What should be in your compatibility equation? What displacement or rotation plus what rotation or our displacement? And the goal is to first find, this is the name, first find MA and then find the rest of the equation, because this is what redundant means. Okay? So think of it. You want to find MA, but the rotation in the given beam at A is 0, but there is certain at some other point. Can you tell me why I'm writing this equation in terms of rotation, this rotation plus that rotation? Why is it so? If you understand this reason, it is not because something was 0, it is because of your choice of redundant. So it is the choice of redundant that dictates your displacement measure. This is the concept I want you to understand. Getting it? It's not about convenience. What can be calculated easily? What displacement or rotation seems easy to calculate? It's not about your choice. It's once you choose your redundant, you are bound to use a certain decompatibility equation. Okay? So if you treat MA as your redundant, there is no other choice except treating that rotation at that point where you remove that MA, the rotation at A as your displacement measure. Okay? Only then MA will be a part of the equation. Only then you can have another structure like this. If MA is not even part of your equation, how can you find it? And the only way you can have MA in your equation is to treat the rotation at A as your displacement measure. Now that is 0. That's the problem. That is 0. The rotation at A in the given beam is 0. It is fixed. It is fixed. Okay? And there is nothing happening at A. There is only problem at other end. So how do you solve it? The hint is that, if you remember, we discussed this case last time, that when you say, how we kept the problem, the same problem last time, we took this as redundant. So how do you go and then remove the load? Because we're considering the case where there's no load, but just assignment. Okay? So you need to understand the concept here. Equal to what is left now? Unit value of RP. So, can you imagine what's happening over here? So, the two displacement profiles that will be generated. So this is one displacement. This is the displacement profile of an actual structure. If this is 0, displacement is 0, it remains straight. Okay? It remains straight, no deflection, no rotation anywhere. But if this is the situation, we have a segment at this end. So this is the displacement profile of the given structure. So the displacement, so it's not just, so we are also using it for the purpose of calculating displacement or rotation at one point in the given beam and then through the principle of superposition. So we are also focusing on just one point, but the principle is valid for all of the points. What I mean by that is, let me try to explain this to you in a different way. So this is the given beam. Let's make it simple. For the current case, I'm saying there's no settlement. Okay, there's just a loading. So when you say this is equal to this plus this, you are actually saying, although we are using it for this point only, but it is valid for all other points. Okay? So displacement in the given beam at this point is equal to displacement in this beam over here and displacement in this beam over here. Okay? We we are using it for this n for a reason. We want to find this unknown. Okay? But as far as the principle is concerned, it is valid for all other points. What does that mean? Displacement at this end, at this point, the given beam is equal to displacement over here plus displacement over here. The principle is valid for all points, although we are using it at certain point for our purpose. That purpose is to find out this RT. But the principle holds for all points. Okay? So if you understand this principle, it means, actually what I want to show you that if you go like that, the displacement profile of the actual structure looks like this. It means the displacement profile that you are getting from here and the one here that you will be getting from here, if you add these two displacement profiles, you will get this profile. At each point, so this displacement is equal to this displacement plus this displacement. I'm not drawing anything to the scale, so it may sound a bit odd to you, but this is what the principle is all about. This whole profile is equal to, so if you draw a line over here, this displacement is equal to this plus this. That's what the principle is. Now, I was telling you that it should be something surprising, something new for you, that you have no loading, you just have displacement and you did the direction at the end. You remember these results? You remember these results? We had certain direction over here, some direction over here, and some more direction. There is no loading. There is just settling. What does that actually mean? What does that actually mean? In the given situation, you are given certain displacement, for example, 40 millimeters downward, and they tell you what is the direction over there. This is what you find last time. Okay? And I think this answer was 103.3 kilometers or so. Okay? Clear? Do you remember this result? The displacement was 40 millimeters downward, and I think it was, can you confirm this, 103 point something kilometers? That was the reaction at B. I'm sorry? 13.3. Only 13.3? Yes. Okay, 13.3 kilometers downward. If you are, if I tell you that there is a 13.3 kilometer load, there's something interesting. If I tell you this is 10 kilometers and I have a downward load of 13.3 kilometers at this tip, what will be the displacement at this end? 40 millimeters. This is what we. So over here I'm telling you, if this is the displacement, guess the force that will be acting over here. And here I'm telling you this is the displacement. So this is the force. What will be the displacement? 40 millimeters. Okay? So coming back to this problem, just one more point. It means the loading does not necessarily look like loads or moments. You don't see any external load, but you see is reaction. Where are they coming from? Just something very important for you to understand. Loading does not always look like forces or moments. It's not always in terms of forces and moments. Loading can also be in terms of imposed displacements. Loading can also be in terms of imposed displacement. You impose certain displacement on that independent structure, you are going to induce certain reactions, certain bending moments, certain shear forces, everything that can be done by applied load. Okay? So it means one way is to apply loads, 30 km per meter, 50 km meter in moments. The other way is to impose displacements. Okay? So you try to understand this point. Imposing displacement is one way of loading a structure. What do you think happens when earthquake shakes a building? Is there anyone pushing the building? No? What's happening? Certain displacements are being imposed at the foundation level, and you see building collapsing. How does it happen? We are imposing displacement, and that is, just a whole new science, a whole new genetic field. But I want you to understand this point. This is something very important for you to understand. This is the concept you need over here. In the primary structure, Will you have any applied loading, any UDL, any moment, any point load? No? Agree? Yes. But we are saying that there is a 40 millimeter displacement at its end. It means this particular primary structure is going like that, 40 millimeter down. Although it doesn't produce any reactions and internal forces. Why? Why? This reaction is zero, this reaction is zero. There's no shear force, there's no bending moment. Why? Yes, can you give me the right technical term? Yeah, you got it, but what would you call this type of structure? Determinate. A determinate structure does not experience any internal forces or any reactions when you impose displacements on them. They will just readjust their geometry, okay? So, you have got displacements. This is the displacement profile for this structure, okay? Get it? And can you get the displacement profile for this structure? This is simpler enough. Simple. This is, unit load. So you can easily get this profile. You've already done this part. Alpha AA, that's what we have been talking about. Alpha AA. Getting it? Equal to L cube over PEI. And the same direction as that's one over here. Getting it? So, the best way to use the table is figure out the magnitude, considering whether it's near end or far end. And the direction is governed by this. Do it for the near end, and for the far end, the magnitude gets half, the direction changes. Okay? So, can you just write down the compatibility equation? Can you just write down? It is exactly the same format as you see over here. That's a big hint for you. Theta A naught. Can I write one here? Will you let me cover? Yes. Theta A naught. Maybe I can write somewhere else. Okay, theta A naught. So I'm getting theta. I'm finding theta primary structure equal to theta A naught plus MA times alpha AA or vice versa. This is the equation. This is not the compatibility equation by now, but this is how you're going to sum up. Where is theta A naught? This is theta A naught. Can you find this? You know this displacement? You know this? So if generally you could call it some other way, this was something called as VB or what? I'm not really sure about that. VB. I think it was called as VB. VB. So if you want to go in terms of VB, you can do that, but I think you can do that. So the value is 40 millimeters, but we can call it VB as general term for this, general parameter for 40. Okay? So this is what theta A naught is. So what is theta A naught? This divided by this. As long as it's a small value, it should be a small value. This is 6 meters, and this is just 40 millimeters. So it's going to be a small value. I'm showing it in an exaggerated way to make it easy to understand. Okay? So it is equal to 40 over. So maybe I could say VB over L. And what about the direction? What about the sign? It is this way. This is what you consider as positive or negative? Oh, yeah, this is clockwise. So this is negative. Minus 2. This is negative, not because this is done, because that's not our parameter. What we're doing is we're calculating this displacement. That's what we were said about. Because we have taken MA is our element. Okay? So this is going to be dq over L. The magnitude of the rotation at this end. What's the sign? It's clockwise or it's negative. So I hope you can understand. A rotation will be positive or negative based on whether it is clockwise or counterclockwise. Okay? So now I hope you can understand. What about theta actual? What is theta actual in the given mean? 0. The settlement is happening somewhere else. Although this is going down due to fixity, there's no rotation at this end. Although as soon as you get out of the end, fixed end, you will start seeing some rotation. But at the end where fixity is provided, it's going to be 0. Okay? This is that minus sign? Okay, so with this is the rotation. Agree? This is the rotation being produced. What is its direction? Clockwise. And we are treating all our equations, this direction is positive for the rotation. So if you treat counterclockwise positive, how should you treat the clockwise? Negative. That's why we have negative sign. So this is how the whole equation actually looks like if I can complete the formal equations. It's theta A naught plus NA alpha AA. And then you see that this is 0. Okay? And theta A naught is equal to minus dB over L, okay, plus MA times L cube over DEI. So that means MA is equal to VB over L into L cube over DEI. So you get this L squared over 3EI. Can you confirm this answer? And it is positive, that means this was correctly assumed to its direction like that. Can you compare the answer to the previous result we got on last Tuesday? Case number 2. Okay, in that case, what we did was, we just found the value of RB, and once we got the value of RB, we calculated the moments in their direction. Okay? But you can still figure it out. Yeah, you can still figure it out. Can you just calculate this thing? L squared means 6 squared. 3 into EI is 24,000 if you remember. Kilometer squared into VD, which is, 40 millimeters, so 0.040. Okay. What is the answer?
2 multiplied by 10 is power 5.
Really? This is 6 squared. I'm doing anything wrong. So, previously we got this answer. Last time we got this answer. Okay, for the second case number 2, we got this answer. So this should be DEI over LBB, same magnitude but opposite direction. And this moment I told you, it should be 3EI over, this was L cube, okay, this was L cube. So this would have been 3EI over L squared. Did I get anything wrong?
Yes, sir.
Oh, actually, I didn't invert this.
Yes, sir.
I was supposed to invert this. 3EI over L cube. Okay. 3EI over L cube. Okay, so now I can correct it. So, what should be this? Can you tell me if this is L cube? What was this? L. This is just L. This is just L. L by AA. This is not L cube. This is just L. Okay? This is just L. So you should be ending up with L squared 3EI over L squared times VB. And this is the same answer that you can end it from here. This force multiplied by L, you will get this point. So L cube that you need to understand. Okay? जहां से आपने रिडंडेंट हटाया है उस पॉइंट पे ही आप कंपैटिबिलिटी इक्वेशन लिखेंगे, और क्या डिस्प्लेसमेंट की लिखेंगे या रोटेशन की लिखेंगे, आपने डिपेंड करेगा वहां से क्या हटाया रिडंडेंट, किसी फोर्स को हटाया या मोमेंट को, जो उसकी डायरेक्शन थी उस या उसकी जो सेंस थी उसी के करस्पॉन्डिंग आपने डिस्प्लेसमेंट मेजर लेना। मोमेंट हटाया था, समेशन ऑफ मोमेंट्स, सॉरी रोटेशंस, जहां से हटाया था उसी पॉइंट पे होगा। नो मैटर की कंडीशन कहां की बने, सब सेटलमेंट की। ओके, ठीक हो गया? निकाल दो। तो अगर आप यहाँ पर कोई अप्लाई करेंगे स्ट्रक्चर पे कोई इम्पोज डिस्प्लेसमेंट